two people order the exact same coffee at the exact same coffee shop on the exact same morning. One of them feels totally normal 20 minutes later. The other one's heart is pounding, their hands are a little shaky, and they can't figure out why today's cup felt so much stronger than usual. Same bag of beans, same size cup, same amount of caffeine, at least on paper. So why did it hit one of them so much harder? That question turns out to be a lot more complicated than most people assume, and it starts with something surprising. Caffeine is the single most widely used mind-altering substance on the planet, and almost nobody treats it like a drug at all. It is legal everywhere. It is unregulated almost everywhere. You can buy it in a gas station, a vending machine, or a supplement aisle without anyone checking your age in most countries, and most of us consume it every single day without a second thought. But underneath that casual relationship is a chemical doing something fairly dramatic inside your brain. Here's the trick caffeine actually pulls off. Your brain has a built-in tiredness signal, a molecule called adenosine, that slowly builds up the longer you're awake, quietly telling your nervous system to slow down and get ready for sleep. Caffeine doesn't give you energy, it blocks that signal. It slides into the same receptors adenosine would normally use, and your brain simply stops hearing the message that says you're tired, even though the tiredness itself never actually went away. That's why the crash feels so real later. The adenosine was building up the whole time. Caffeine just muted the alarm for a few hours, and eventually the volume comes back up all at once. It moves through your body fast too. Within about 45 minutes of drinking it, almost all of the caffeine you swallowed has already made its way into your bloodstream, and from there it crosses straight into your brain. So if caffeine works that fast and that predictably, why does it still feel so wildly inconsistent from person to person, or even from one day to the next for the same person? Before we get to that, here's a question worth sitting with for a second. How much coffee would it actually take to kill someone? The honest answer is a genuinely enormous amount. Researchers estimate the lethal dose of caffeine sits somewhere around 5 to 10 grams in a single sitting, and a typical cup of coffee only has roughly 1/10 of a gram in it. Do the math and you'd need somewhere close to 100 cups consumed in a short window before caffeine on its own became life-threatening. Nobody drinks their way there by accident with coffee alone. It usually takes concentrated powder or pills to get anywhere close, which is exactly why health agencies warn so heavily against those specific products. So the danger was never really about coffee killing you outright. It's about something much smaller and much more common: the jittery hands, the racing heart, the wired feeling that won't let you fall asleep that night. And that brings us back to the real mystery. If the dose is roughly the same, why does the experience change so much from body to body? For decades, the standard advice in sports nutrition has been to dose caffeine by body weight, the same way you dose a medication. A modest amount sits around 3 milligrams for every kilogram you weigh. A stronger performance dose around 5 to 6, and anything above 7 counts as a high dose. That formula sounds precise. It sounds like it should work the same way for everyone, as long as you scale it to your size. A heavier person gets more, a lighter person gets less, problem solved. Except caffeine doesn't only care about how much you weigh, it cares about what you're made of. Here's why that distinction actually matters. Once caffeine gets into your bloodstream, your liver has to break it down, mostly turning it into another compound that does a lot of the same adenosine blocking work caffeine does. Only a small remaining share turns into 2 other, milder relatives you've probably also swallowed without realizing it, the same compounds found naturally in chocolate. But here's the part that gets interesting. Fat tissue in the body doesn't just sit there. It can act almost like a sponge, soaking up certain compounds and releasing them slowly over time, instead of letting the liver clear them out quickly. And caffeine's breakdown may not run at the same speed in every body either. Some research going back decades has hinted that people carrying more body fat process caffeine more slowly. absorb it faster into the blood, and hang on to it longer once it's there. If that's true, then dosing caffeine purely by total body weight might be quietly getting the math wrong for a huge number of people, not because the formula is careless, but because weight and body composition are not actually the same thing. Think about two people who weigh exactly the same number on a scale. One of them carries that weight mostly as muscle. The other carries more of it as fat. Their bodies handle nutrients, medications, and yes, caffeine in genuinely different ways. If stories like this, ordinary habits turning out to hide a genuinely different chemistry underneath, are the kind of thing you find interesting, this channel digs up a new one every week, and hitting subscribe means you won't miss the next one. Now, back to what else changes how caffeine behaves in your body. Body composition isn't the only wild card either. Buried in your DNA is a single gene that controls how fast your liver processes caffeine in the first place, and depending on which version you inherited, you can burn through it dramatically faster or slower than the person next to you. Slow metabolizers hold on to caffeine so much longer that a single afternoon coffee can still be circulating in their blood well into the night, quietly wrecking their sleep without them ever connecting the dots. Fast metabolizers can drink a coffee an hour before bed and barely notice it. Same drink, same time of day, completely different night. Then there's tolerance. Drink caffeine often enough and your brain starts building extra receptors to compensate, which is part of why regular coffee drinkers often feel less jittery than someone who almost never touches the stuff and suddenly has a large one. That's also why the person who says they never drink coffee and finally caves for one at a party is usually the one still wide awake at 2 in the morning, staring at the ceiling. And here's where it gets a little ironic. Caffeine is one of the most common ingredients in fat-burning supplements, marketed heavily to people trying to lose weight, which means some of the people taking the highest doses may be exactly the group whose bodies hang on to that caffeine the longest. Sex seems to play a role too, though the science there is messier. Some studies suggest men and women process caffeine somewhat differently, but not consistently enough for anyone to write a separate dosing chart for it yet. Because here's the thing. For a long time, this idea that body fat specifically, not just total weight, changes how caffeine behaves in your blood was mostly theoretical, suspected, debated. Nobody had actually measured it directly. So which was it? Was body fat actually going to change how much caffeine ended up in someone's blood? Or was this just an old theory that never really held up? A research team decided to actually test it, instead of just assuming the old body weight formula was close enough. The setup was simple on purpose. Take a group of women, split them into two groups, not by how much they weighed, but by their actual body fat percentage. One group under 30% body fat, the other group above it. Give every single person the exact same relative dose of caffeine, scaled to their own body weight. The same moderate dose sports nutrition guidelines already recommend. Then wait exactly 1 hour, the point where caffeine typically peaks in the blood, and draw a blood sample. No guessing, no self-reported symptoms, just a direct chemical measurement of exactly how much caffeine and how much of its main breakdown product was actually circulating in each person's bloodstream. So, after the exact same relative dose, who ended up with more caffeine still swimming around in their blood an hour later? The group with higher body fat did, and it wasn't a small difference. Their caffeine levels came in at more than 4 times higher than the leaner groups, even though everyone had taken the exact same dose adjusted for their own weight. The main breakdown product, that adenosine-blocking compound your liver makes from caffeine, was significantly elevated too. The only chemical that barely moved between the two groups was one of the milder, chocolate-related relatives. When the researchers looked at what actually predicted those differences best, body weight alone barely mattered, and age barely mattered. It was body fat specifically that explained the overwhelming majority of the difference. None of this means caffeine is dangerous for people carrying more body fat. And it doesn't mean everyone needs to start measuring their body fat percentage before their morning coffee. This was one dose, measured at one point in time, in one specific group of participants, and the researchers themselves are upfront that a bigger, more varied study is the natural next step. What it does suggest is a real, physical explanation for something a lot of people have quietly suspected about their own bodies for years, that the same cup of coffee simply doesn't land the same way for everyone. So, the next time a coffee hits you differently than it hits the person next to you, that might not be in your head at all. It might just be your own chemistry, quietly running the numbers a little differently than theirs.